This means you'll be able to create a visual representation of these relationships. So, what are these implicitly defined functions, and how are they different from what we usually work with? Think back to the functions you're familiar with, like y equals 2x plus 1. This is an explicit function. We say it's explicit because the variable y is isolated on one side and the expression involving x is on the other. It's a straightforward rule that tells you exactly how to find y for any given x. This explicit form makes it clear that for every single input x, there's exactly one output y, which is a key characteristic of a function. Now, let's look at an equation where it's not so easy to isolate y. Consider the equation x squared plus y squared equals 9. We call this an implicit equation because the relationship between x and y is implied, or mixed up together, rather than stated explicitly as y equals some function of x. If we try to solve for y, we get y equals plus or minus the square root of 9 minus x squared. Notice the plus or minus. Because of this plus or minus, a single x value, like x equals 0, gives us two possible y values, plus 3 and minus 3. Since one input, x equals 0, gives two outputs, y equals 3 and y equals minus 3. This relation, as a whole, is not a function. However, the original equation, x squared plus y squared equals 9, still defines a perfectly valid graph. The graph of this equation is a circle with its center at the origin and a radius of 3. This graph, despite not being a function itself, is said to be implicitly defined by the equation. So, to recap, an implicitly defined relation is an equation involving two variables where it's not solved for one variable in terms of the other. An implicit equation can describe one or more functions. So, how do we construct a graph of an equation like this? We have two main methods. First, we can plot solutions. This is the most direct way and works for any implicit equation. The second method, which is often faster but only works for some equations, is to solve for one variable and then graph the resulting function or functions. Let's start with our first objective, using the direct method of plotting solutions. The process is simple. You choose a value for one variable, plug it into the equation, and solve for the other. Each pair you find, x, y, is a point that lies on the graph. For our example, x squared plus y squared equals 9, let's find some points. We'll start with easy ones. If x is 0, we get y squared equals 9, so y is plus or minus 3. This gives us 2 points, 0, 3, and 0, minus 3. Similarly, if y is 0, we get x squared equals 9, so x is plus or minus 3. This gives us 2 more points, 3, 0, and minus 3, 0. These are the intercepts of our circle. We can find more points by choosing x values between -3 and 3. For example, if x is 1, y is plus or minus the square root of 8. If x is 2, y is plus or minus the square root of 5. Plotting these points and connecting them with a smooth curve reveals our familiar circle. As you can see, this method always works. Now let's look at the second method for graphing, which we mentioned earlier, solving the implicit equation for y. We've already done this for x squared plus y squared equals 9. We found that y equals plus or minus the square root of 9 minus x squared. This single implicit equation gives rise to two explicit functions. The first function, y sub 1 equals the square root of 9 minus x squared, is the top half of the circle. This part of the graph is a function because for every x there's only one y. This is often called the principal function because we take the positive square root. The second function, y sub 2 equals negative the square root of 9 minus x squared, is the bottom half of the circle. This is a separate, valid function on its own. The beauty of this method is that we can now use our understanding of function graphs. We know how to find the domain of each square root function, and we know they will form a smooth curve. By graphing these two functions on the same set of axes, one above the x-axis and one below, we reconstruct the complete graph of our original implicit equation, the circle. Let's try a more complex example. How would we graph x equals the quantity y squared minus 2 squared? It looks complicated, but it's perfect for our methods. Let's start with method 1, plotting points. Instead of choosing x values and solving for y, which would involve square roots, let's choose y values and solve for x. This is the advantage of the direct plotting method. You can pick the easiest path. A value of y equals 0 gives x equals 4. A value of y equals plus or minus the square root of 2 makes the inner part 0. so x equals 0. What happens when y is 2? X is also 4. What about when y is negative 2? X is still 4. This pattern is important. Let's use method 2 and solve for y to understand this better. First, take the square root of both sides to get the square root of x equals y squared minus 2. Notice we only need to write plus or minus the square root of x if we were solving for y squared. Here, we can proceed directly. Add 2 to both sides, and then take the square root again. This gives us y equals plus or minus the square root of 2 plus or minus the square root of x. Our single implicit equation has given us 4 different explicit functions. Each one corresponds to a different piece of the graph. When we plot all 4, we see a shape that resembles the letter W rotated onto its side. Now that we can graph implicit relations, let's explore our second learning objective: how the two variables, x and y, change together. This is a key part of understanding the relationship between the quantities. We can describe how x and y vary by looking at the slope, or the ratio of their changes, delta y over delta x. Consider the graph of x squared plus y squared equals 9 again. Let's look at the first quadrant of the circle. As x increases, from 0 towards 3, what happens to y? You can see that y is decreasing. Since x is increasing and y is decreasing, they are changing in opposite directions. We call this an inverse variation. Mathematically, the ratio of the change in y to the change in x, delta y over delta x, will be negative because the numerator is negative and the denominator is positive. So, a negative ratio tells us the variables are varying inversely. Now let's look at the third quadrant. Here, as x decreases, moving from negative 3 towards 0, what does y do? It also decreases, moving from 0 towards negative 3. In this case, x and y are changing in the same direction. We call this a direct variation. The ratio delta y over delta x will be positive, because a negative number divided by a negative number gives a positive. So, a positive ratio means the variables are varying directly. We can see this principle hold true all over the graph. It's a powerful tool for understanding how things are changing. Finally, let's explore some special cases of how variables change. When the rate of change is 0. We can have horizontal intervals or vertical intervals, and these correspond to 0 rates of change in one of the variables. Let's use our circle example again. X squared plus y squared equals 9. On a circle, the slope, or the rate of change of y with respect to x, is not constant, but at the very top and bottom points, the tangent line is perfectly horizontal. The slope is 0. This means for a tiny change in x around these points, the change in y is 0. The circle is momentarily flat. So, a horizontal interval is a place where the rate of change of y with respect to x is 0. On our circle, these are the points where x is 0, which are 0, 3, and 0, minus 3. What about the sides of the circle? At the points 3, 0, and minus 3, 0, the tangent line is vertical. This means the slope is undefined, because a tiny change in y causes a 0 change in x. The rate of change of y with respect to x goes to infinity. We can describe this as a vertical interval, where the rate of change of x with respect to y is 0. This means for a tiny change in y, the change in x is 0. In other words, the x-coordinate is not changing. We see that understanding these special cases helps describe the graph's behavior at key points. Let's summarize what we've learned today about implicitly defined functions. First, we learned that an equation like x squared plus y squared equals 9 implicitly describes a relationship between x and y. While it's not a function on its own, it can define several functions. Second, we saw that we can graph these equations in 2 main ways. We can plot points directly, or we can sometimes solve for y to get explicit functions and graph them. Third, we learned to analyze how the variables vary together. A positive ratio of changes means they increase or decrease together, while a negative ratio means one increases as the other decreases. This is a crucial concept for calculus. Finally, we explored horizontal intervals, where y's change with respect to x is 0, and vertical intervals, where x's change with respect to y is 0. You now have the tools to analyze these types of complex but very common mathematical relationships. Great job!